here. And well, welcome everyone to this week's Durham Geometry and Topology seminar. So it's a pleasure to have David Wraith from Maynooth University in Ireland. He will talk about highly connected manifolds and intermediate curvatures.
Okay, well, first of all, thanks very much for the invitation to speak in this particular platform. Having been on your mailing list for a little while, I've noticed the great diversity of talks that have been appearing here over the last weeks and months, and so I thought it may be worth. I mean, it's not clear what the audience is, but if the audience is fairly diverse, I thought it may be worth spending a few minutes at least talking about where I'm coming from a geometric point of view. So I'm a Riemannian geometer. I think about manifolds usually, but not always, closed and smooth, with Riemannian metrics, which of course provides geometry, and in particular provides a notion of curvature, which is going to feature heavily in this talk. So first of all, before I forget, this is some joint work with Diarmuid Crowley, and if you dig down to the very basic kind of underlying questions, what I'm interested in is trying to understand the interaction between geometry and topology on manifolds. I mean, it's fairly clear that if you have some sort of geometry in mind, this is going to restrict the kind of manifolds which can display that geometry. Conversely, if you understand the topology of a manifold, there is this question about what kind of geometric features this manifold can be endowed with. Now, a particularly important, historically, special case is to understand the topological implications of various kinds of curvature conditions. And amongst curvature conditions, perhaps the most natural are the sign-based curvature conditions. So looking at positive or negative kinds of curvature. So the curvature has, I mean, there are various ways of interpreting the word curvature, but the classical ways of doing that involve the so-called sectional, Ricci, and scalar curvatures, and these have been studied in relation to the understanding the topological implications of sectional, Ricci, or scalar curvature conditions. I mean, this goes back quite a long way historically. So just in case, I mean, probably all of you are familiar with these notions of curvature, but just in case you're not particularly comfortable with these things, let me just say very quickly a couple of words about them. So when we learn geometry first, you meet the Gaussian curvature in the world of surfaces. And this, of course, tries to interpret in a mathematical way what we intuitively understand by the word curvature. And if you move to higher dimensional objects, then the natural generalization of this is the sectional curvature. So all you're doing here is you're choosing, if you like, embedded two-dimensional surfaces within your manifold and looking at the Gaussian curvature of those in some sense. However, in higher dimensions, you have the option of doing some sort of averaging process. And so the Ricci curvature is obtained as an average of sectional curvatures. And if you're not familiar or comfortable with this, you can think about this as being curvature in a tangent direction. So of course, your manifold can curve in different ways in different directions, and the Ricci curvature tries to capture this idea. Now, technically speaking, it depends quadratically on the tangent vector, on the length of the tangent vector you look at. And as a quadratic form, there is a corresponding symmetric bilinear form, which is called the Ricci tensor. And the Ricci curvature and the Ricci tensor will appear in significant ways later on in this talk. You could also average over the various directions and end up with a single number at each point on the manifold. And this is the scalar curvature, which is a smooth, real-valued function on your manifold. So as you pass from sectional to Ricci to scalar, you're doing an averaging process. So in some sense, you're washing out the geometric content that's contained in these notions of curvature. So when you get to scalar curvature, almost all the geometric content is washed out, but there is still something of interest remaining. And I'll say a little bit more about that very shortly. So this is how to think about, in particular, the Ricci curvature, which we're going to be dealing with, is curvature in a direction. It's essentially a quadratic form on the tangent bundle, and the Ricci tensor is a corresponding symmetric bilinear form. So again, keeping with some intuitive basics, the Gauss-Bernay theorem, which I assume people will have seen before, expresses for surfaces the integral of the Gaussian curvature. And very nicely shows up this dichotomy between topology and geometry. You have this tension in general that we're trying to understand between the two, but in the case of surfaces, you have this very nice equation, and the left-hand side is geometric and the right-hand side is topological. And so very clearly you see this relationship between curvature and topology. However, in high dimensions, the situation is far less clear. So just a simple consequence, if you're interested in positive curvature, which is the kind of thing we're going to be interested in, then you see straight away that only this two-sphere and the real projective plane can admit positive Gaussian curvature. Now, in higher dimensions, it turns out, due to a result from the early mid-90s due to Joachim Lohkamp, that in fact there are no topological obstructions to either negative scalar or in fact negative Ricci curvature, dimensions at least 3, and this applies to both compact and non-compact cases. So in some sense, if you're trying to understand this topology geometry dichotomy, the case of negative scalar or negative Ricci curvature is actually not interesting. However, it's a very different story if you flip around the inequality sign and think about positive curvature, positive scalar, positive Ricci, positive sectional, whatever. And what you see is there is a sharp dichotomy, asymmetry, that's the word I'm looking for, between the positive and the negative cases. And in fact, there are, as I'll mention in a second, real obstructions to admitting basically any form of positive curvature. Now, just at the bottom of the screen, I thought I'd throw this in somewhere. In case I forget, all the manifolds in this talk will be closed, smooth, Riemannian, and have dimension at least 5. I mean, strange things can happen in dimensions 3 and 4, which is somehow exceptional. I'm a high dimensional geometer, so everything is starting for me in dimension 5 and above. So I referred a second ago to the fact that positive kinds of curvature are generally topologically obstructed. And in the case of positive scalar curvature, for simply connected manifolds, dimensions at least 5, then the implications are fully understood. And this was work going back to the sort of 80s and early 90s by a bunch of people, Stefan Stolz, Gromov and Lawson, and other people who were involved too. And so the situation for positive scalar curvature, simply connected manifolds, dimension at least 5, is essentially understood. However, if you start thinking about different kinds of fundamental groups, the full picture, I mean, we know lots of things, but the full picture is still as yet incomplete. Now, moving to Ricci curvature, which is the thing I'm most interested in, the topological implications of positive Ricci curvature are essentially still fairly mysterious. I mean, what do we know? I mean, well, positive Ricci curvature implies positive scalar curvature, so we obtain obstructions coming from positive scalar curvature. And we also know that by the classical Bernay-Myers theorem, that the fundamental group of a closed Ricci positive manifold has to be finite. But that's essentially all we know. I mean, what else is out there? I mean, chances are there are other topological consequences of positive Ricci curvature, but as I've mentioned, these somewhat remain mysterious. So moving towards the work I want to talk about in the remainder of the talk, there's this kind of idea that a simple topology might facilitate the existence of nice geometry, and in particular, for example, positive Ricci curvature. When we think about the basic examples of manifolds with positive Ricci curvature, you might think about spheres, projective spaces of various types. These are all topologically, in some sense, simple. I mean, they have lots of symmetries too, but there's this sort of idea, which has its limitations, as I'll discuss on the next slide, but maybe simplicity from a topological point of view might aid, or at least might help with constructing metrics or nice geometries. So one part of the title of this talk involved the phrase highly connected manifold. So let me say something about that. So a standard definition going back decades is that a manifold is highly connected if it's n-1 connected, if the manifold has dimension either 2n or 2n plus 1. So in other words, we're connected up to the middle dimension. So all the kind of lower homotopy groups all vanish. So spheres are the basic and most obvious examples of highly connected manifolds. However, so are exotic spheres. So these are spheres which are homeomorphic, but not diffeomorphic to the standard sphere. Now, this is one has to, I mentioned there are some limitations to this idea that simple topology might facilitate nice geometry. If you think that spheres, at least topologically, are nice, then, well, you might think that exotic spheres being topologically, not smoothly topologically, but topologically, if you see what I mean, are simple. But as you can see, these results of Hitchin going back to the 70s, which suggests that exotic spheres might not be quite so nice after all. So there are examples of so-called Hitchin spheres, which occur in dimensions 1 and 2 mod 8, which don't even have positive scalar curvature. So, I mean, these are very, very kind of weird objects, despite being homeomorphic to the standard spheres in those dimensions. So this idea that simple topology might facilitate nice geometry is a compelling idea, but one has to be careful with pushing this idea too far. For the record, an old result of mine, dating from my thesis, shows that all homotopy spheres, so standard or exotic, which bound a parallelizable manifold, so bound a manifold with a trivial tangent bundle, these all admit metrics of positive Ricci curvature. And this is a large subfamily of all homotopy spheres. Okay, but a full understanding, just thinking about positive Ricci curvature, a full understanding of which homotopy spheres admit or which don't admit positive Ricci curvature is currently well out of range of our present understanding. Okay, so a key background result for the main things I want to discuss in this talk is a theorem of mine with Diarmuid Crowley from a few years ago. And we were looking at these highly connected manifolds in dimension 4k-1, starting in dimension 7. There's an extra technical requirement about parallelizability, and let's not worry too much about that in certain dimensions. But it essentially says that in these dimensions, highly connected manifolds up to potentially doing a connected sum with a homotopy sphere, then these manifolds admit positive Ricci curvature metrics. So, as we saw from the previous slide, one has to be a little bit careful with dealing with exotic spheres. Now, the Hitchin spheres don't appear in these dimensions, but there still could be other exotic spheres which maybe don't admit positive Ricci curvature that we simply don't know about at the moment. So this ambiguity, this up to connected sum with a homotopy sphere is unavoidable at present. So the techniques behind this, I don't want to say too much about it. I mean, for the record, if you know about these things, the manifolds in question in this theorem are constructed via plumbing of disk bundles. But the techniques involved also throw up results in dimensions 4k+1. But there's a problem with that in that it only throws up manifolds in dimensions 4k+1 with torsion-free integer cohomology. And this might sound like it's not a big deal, but actually it is a very big deal, because what it means is the manifolds you get in dimensions 4k+1 belong to a very short list of well-known examples. You have spheres, products of spheres, connected sums of products of spheres, and that's about it. And all of these are already known to emit positive Ricci curvature. But these are really a drop in the ocean amongst all the highly connected manifolds in dimensions 4k+1. So what can you say about the curvature of the remaining manifolds which are highly connected in this dimension? So as a prerequisite to being able to understand the geometric question, we have to start with a topological question. What can we say about the topological structure of these manifolds? After all, if we don't have any means of understanding how these manifolds are constructed, we have no means of actually getting our hands on the geometry. So there's a lot of words involved on your screen right now, but let me try and just talk you through the key points of this topological theorem. So your highly connected manifold in dimension 4k+1, up to connected sum with a homotopy sphere, takes kind of one of two sort of forms. One of the forms I'm calling M0, and this is going to be a nice manifold. So this is something we understand. This is actually something that we've kind of understood geometrically for a long time. It's either going to be a sphere, or it's going to be a sphere bundle over a sphere, so specifically an S2K bundle over an S2K plus 1 base, or it's going to be a connected sum of these linear sphere bundles. So M0 is something we actually understood from a geometric point of view quite nicely. Or, on the other hand, we could have M0 connected to a bunch of other things I'm calling M with a positive subscript. And the M with a positive subscript is constructed topologically in a very nice way. You start with a 4K plus 1 sphere, and you embed into that a pair of 2K spheres. And then you perform surgery on those 2K spheres, and this produces one of these MIs for I positive. Now, there are two words in that, or I should say a little bit more about in case people aren't familiar. So the idea of spheres being linked, at least in these dimensions being linked, is sort of the obvious thing. I mean, you can think, I'm guessing you can probably see my camera, that you can, in R3 or in S3, you can think about a couple of circles. These have the right dimensions, and so they're disjoint, but you can also link them so they join together. And of course, if I could do it with my fingers, and I can't, you could wind one circle around the other in kind of a torus knot, and that would be linked in a more complicated way. So the linking number expresses how linked, in some sort of sense, these spheres are. So what you do to compute the linking number is you bound one of the embedded spheres with a disk, and by maybe adjusting the disk and the other sphere slightly, you can get them into general position so they intersect transversely, and then you simply count the oriented intersection number between the disk and the other sphere. So it's a very simple kind of idea and expresses what you would understand in an intuitive sense by things being linked. The other word that I mentioned a second ago is surgery. So the idea here goes like this. You have an embedded sphere within a manifold, and let's assume, it doesn't have to, but let's assume it has a trivial normal bundle. In that case, you can cut out a tubular neighborhood of your embedded sphere, which is a product here of a sphere cross a disk. And you can glue in a sphere cross disk, but somehow the other way around. So the point here is that the thing you're cutting out and the thing you're gluing in, they have a common boundary. So this gives you a way of topologically altering the manifold which you start out with. And this is the result of performing a so-called R surgery on the manifold. So for these, going back a slide a second, these M1, M2, M3, M4, and so on, these are, you start with a sphere, you have a link with some linking number, which is coming from the topology, and you perform surgery on both of those spheres, okay, which are linked together. So that's the idea, and that creates these manifolds MI. Just one technical point that if anyone's interested. So the surgery construction requires us to specify a trivialization of the normal bundle. And different trivializations can produce different manifolds when you complete the surgery process. This is to do with how you glue the thing in. There are different ways you can glue the thing into the hole you've created. Okay, small technical point, but just for the sake of completion, I thought I should mention this since I will mention it again later on. So the topological result, I don't want to go into the details of this, but let me just talk about the idea of the proof for a second. So you start with your highly connected manifold, and up to connected sum with a homotopy sphere, this can be decomposed as well. Rather, you can view this as the boundary of a handle body, so something constructed out of handles. Now, this is very, I'm not going to go into the details here, but this is very 1960s topology going on here. And indeed, the topological result I had on the previous screen is built upon on the topology that was developed by Terry Wall back in the 1960s. And one of the nice things about this whole situation is that you can classify these handle bodies that arise by an algebraic tool called the extended intersection form. So this is a really kind of beautiful situation where the topology and the algebra mirror each other exactly. And so you really can, and it's not just approximation, you can really capture all the details. And then there is an algebraic decomposition of these so-called extended intersection forms. And then by examining what you get in an algebraic decomposition, you can simply read off the topological structure which was in the theorem about these connected sums of these different pieces. So this is all based on work of Wall from the 1960s. Now, turning our attention back to curvature in geometry, one thing that has to be said at the outset is that connected sums, which after all is the simplest kind of topological kind of construction out there. So you just remove a disk from each of your manifolds and glue the remaining things together. This has a difficult relationship, if you like, with positive Ricci curvature. So it's a classical result from the Bernay-Myers theorem that if you have two manifolds with finite fundamental group, then the connected sum will have an infinite fundamental group, and by the Bernay-Myers theorem, this means that you can't have positive Ricci curvature. So in general, the connected sum of positive Ricci curvature manifolds does not support positive Ricci curvature. However, in the simply connected case, which is what we're dealing with now, we have no real idea. There are examples in the literature, but it's generally unknown, and it seems to be a very difficult problem to understand when you can extend positive Ricci curvature over a connected sum. So the long and short of it is our main topological theorem for our highly connected manifolds in dimensions 4k plus 1, because our decomposition involves connected sums, the theorem doesn't really help us show the existence of positive Ricci curvature metrics. So this tells us that the analog of the motivational result in dimensions 4k minus 1, I've mentioned a few minutes ago, is kind of out of range at present. Which leads me nicely on to a notion of intermediate curvature. So this was the second thing in my talk title. So a manifold has k positive Ricci curvature, which I'm going to use Ric sub k as the symbol, if the sum of the lowest k eigenvalues of the Ricci tensor, I mentioned this earlier, is positive at every point, or if you like, the sum of any of the k eigenvalues is positive. Now, this was a notion introduced, I don't know, maybe best part of 20 years ago by John Wolfson. And this has caught my attention because what it does, it gives you a nice family of curvatures which interpolate between positive scalar curvature on the one hand and positive Ricci curvature on the other hand. So Ricci positivity is equivalent to one positive Ricci curvature, and for an n-dimensional manifold, positive scalar curvature is equivalent to n positive Ricci curvature. Now, there are similar notions of intermediate curvatures between, say, positive Ricci and positive sectional, and these have attracted quite a bit of attention in recent years. And one consequence of this, which has been unfortunate, is the name of these curvatures and the symbol to denote them have become a bit confused. So you will see other papers in the literature with Ric subscript k meaning something else. And anyway, so I don't want to go into that, but for the purposes of this talk, these curvatures, these intermediate curvatures, lie between scalar and Ricci, and they are defined in terms of the sum of the lowest k eigenvalues being positive at each point on your manifold. Okay, so we get a natural family of curvatures. And so what this is allowing us to do is have, if you like, a more nuanced viewpoint of the classical curvatures. You kind of, if you like, take a few steps back and have a wider picture of what's going on beyond the three classical scalar, Ricci, and sectional curvatures. You see more, and that, I claim, can only be a good thing. Now, for the remainder of this talk, I'm going to concentrate on two positive Ricci curvature. So this means the sum of the lowest two Ricci eigenvalues is positive. So this is as close as you can get to positive Ricci curvature without necessarily being positive Ricci curvature. So we're allowing ourselves at most one bad direction in the sense of being Ricci negative, but that can't be too bad. It can't be any worse than the lowest positive Ricci curvature direction is positive. Okay, so you could have some negativity, but only in at most one direction and only in a carefully controlled quantity. So I mentioned John Wolfson coined this idea of K-positive Ricci curvature, and he proved a lemma. This is part of a wider theorem, but this is the only case we actually need. That if you have a pair of manifolds with two positive Ricci curvature, then the connected sum also admits two positive Ricci curvature. So this automatically gets away or overcomes the biggest difficulty with our topological result for our highly connected manifolds and positive Ricci curvature. Within this new curvature condition, we can do connected sums. So this offers a possibility of proving a theorem about two positive Ricci curvature for our highly connected manifolds. And indeed, this is the theorem. So highly connected manifolds, dimensions 4k plus 1, up to, as usual, the connected sum with a homotopy sphere. All these manifolds, there's this parallelizability technical condition, but don't worry about that. All these manifolds admit metrics of two positive Ricci curvature. So this is as close as you can get to being positive Ricci without being positive Ricci, if you like. So, so this is the result I want to discuss for the remainder of the talk. So how can we go about dealing with this? Well, of course, it comes down to our main topological decomposition result. So the M0s I mentioned a while ago, so we had this M0, which was either a sphere or linear sphere bundles over spheres or connected sums of sphere bundles over spheres. These are all known to admit positive Ricci curvature. Connected sums are okay within two positive Ricci curvature. So everything boils down now to looking at these things I called Ni for I positive. These were the things constructed by performing surgery on links of pairs of spheres. If we can show that these building blocks admit two positive Ricci curvature, then we prove our main theorem. Okay, so that's what we're going to set out to show for the remainder of the talk. Right. So let's talk about surgery on links. I mentioned earlier there was these results about positive scalar curvature. And for example, we understand topologically what's the implications of positive scalar curvature in dimensions at least 5, at least in the simply connected case. And surgery is one of the principal tools behind proving these results for positive scalar curvature. Now, you might then ask, can you do similar kinds of, are there similar results discussing how surgery, or should I say positive Ricci curvature behaves under surgery? And there are some, but they're highly limited. And so you would hope then, and indeed is the case, that if you weaken the curvature conditions slightly, you can do surgery preserving the curvature condition in a slightly, more, it becomes slightly easier. Okay, so how do you do this? The key is to start with an appropriate metric on the sphere, on the ambient sphere. Now, by writing this, I'm subliminally telling you the metric you start out with on the sphere is not going to be round. If you try and start with a round metric and then embed your spheres appropriately within that ambient sphere, I mean, the metric that you get induced on the spheres on which you want to produce surgery is somehow uncontrollable and probably very nasty. So you need to start with an appropriate metric in the ambient setting that will help you do surgery on this pair of linked spheres. So the starting point is to think about the sphere as a double warped product. You can think about the sphere. So if you take out a couple of points, you can, the remainder you can think about, maybe you should have an open bracket here if you've removed a couple of points, as an interval cross a pair of two K-spheres. And to distinguish them, I'm going to call them sphere A and sphere B, because you have the same dimension. There's no other way of distinguishing them. Now, if you think about the round metric, it's a well-known fact that this can be expressed as a double warp product where you have scaling factors sine squared and cosine squared. So we're thinking about the sphere in that case topologically like this, and then you have you could describe the metric like this. And of course, you get some kind of collapsing going on at the endpoint when t is 0 and t is pi over 2, but that gives you a well-defined metric on the sphere. Now, our metric, our ambient metric, is going to be described by the diagram which is coming up next. Now, V and W are going to denote the spheres we're going to perform surgery on. So they're going to be in this picture, which you will see right now. Now, let me try and interpret what this picture is saying. At the two ends, just ignore the middle bit for the moment. At the two ends, what you have is a picture of scaling functions. So I've got my t, my parameter little t, running along the axis, the horizontal axis. And I've got a scaling function there, which looks a bit like a sine on the left and a constant scaling function, and something a bit similar on the right-hand side. So these are scaling functions which are going to go into a double warp product. So near the ends of this picture, we're going to have a double warp product. Now, in the middle of this picture, we're going to have a product metric with dt squared plus something, and the g is a metric on, if you like, a vertical slice through this picture. And the vertical slice is SA cross SB. Okay, so any slice through this picture, apart from the two endpoints, you have SA cross SB as being your vertical slice. So G is a metric, some metric I'll come to in a minute, on SA cross SB. And then you have to transition between the warp products at the outside and this metric in this middle segment. Okay, so the question is, what is this metric G? Now, V, by the way, is going to be a sphere which you see at the end here, which is going to correspond to a copy of SA. And then W is going to be in this middle slice, but I need to discuss what W is in a second. So first perform surgery on this sphere V. And we're going to assume, as my picture indicated, we have a warp product metric. One of the scaling functions looks like a sine, the other is constant. And it's a lemma essentially due to Shah and Yang back in the 90s, that if this constant is sufficiently small, then you can perform surgery preserving positive Ricci curvature locally. And so this is even better than two positive Ricci curvature. You can work within positive Ricci curvature as far as that particular sphere is concerned. The problem, and it is a problem, then comes with this second sphere W, which is somehow linked around the sphere V. It's twisted around it somehow. So we have to be able to locate it and understand it from a geometric point of view, and then perform surgery on that, preserving this curvature condition. So let me tell you what I'm going to choose for my second sphere W. As I mentioned before, it's going to be in the middle of this picture. So that was the slice when t is capital T over 2. But the key thing is that the submanifold W is just the graph of a function. Okay, it's specifically a graph of a smooth degree D function from the sphere SA to the sphere SB. So you pick any smooth degree D map, you think about its graph sitting in that middle slice of my previous picture, and I claim that this will serve as a manifold W. And it's essentially straightforward topological computation to show that the linking number between V and W is just the degree of the map you've used to construct the embedding W in the first place. Now, the embedded manifold W has some interesting topology, sort of ambiently speaking. So the normal bundle has Euler number 2D. And so this tells you, at least if D, the linking number, is non-zero, this normal bundle is non-trivial. Okay, so this thing is really kind of twisty somehow within this slice SA cross SB. However, looking at looking at things in a wider perspective, it's stably trivial. So if we had a trivial line bundle to that normal bundle, it trivializes it. Which is of course good, because we want to do surgery on W within this ambient manifold. So we are in effect, the normal bundle in the ambient manifold is the stabilization of the normal bundle in this slice SA cross SB. And we need triviality to be able to do surgery. So now, each point in this W is the graph of a function from SA to SB. You can think about each point in that graph as being the center of a hemisphere within the SB. And what's going on here is that W, being a graph, and this is why being a graph is important, it's transverse to the SBs. Remember, F is a map from SA to SB, so W is transverse to the SBs in this product SA cross SB. And so this means that the bundle of hemispheres provides a nice model for the normal disk bundle. Now, you can project, just in the obvious way, from SA cross SB, from this middle slice of my previous picture, down to this manifold W. And what this is a trivial sphere bundle. It's a trivial SB bundle over W. However, it is constructed as the double of a non-trivial disk bundle. So there's something interesting topologically going on here. You've got a non-trivial disk bundle, which then doubles in the obvious way to give you a trivial sphere bundle. And you can see the triviality of the sphere bundle because this map pi, this projection to W, it's the standard projection of this slice onto SA factors through pi. So it's clearly a trivial sphere bundle, but it's a double of a non-trivial normal disk bundle. So our problem geometrically is to try and construct a metric G, I called it, on this SA cross SB, on this slice through my ambient sphere, which reflects all this interesting topology. So that's our task. Now, let me quickly go through how we construct this. I've got a picture on the next slide which tries to indicate this in a slightly friendlier fashion. But what I'm going to do is I'm going to construct a submersion metric. So it's a submersion metric with totally geodesic fibers. So if you're not familiar with submersion metrics, think about a bundle. If you give a metric on the base and a metric on the fiber, then somehow this suggests a metric on the total space. But in order to actually give a metric on the total space, you need to talk about the directions which are orthogonal to the fiber. So you need some extra information too. And there's a very standard construction for these submersion metrics. They're kind of metrics which are naturally adapted to bundle structure. That's how to think about it. And you need some data. You need a metric on the W, which we can take to be round, a metric on the fiber, which is going to be one of these SBs, and you need some extra information which describes where the so-called horizontal distribution lies. And the standard way of doing this is by introducing a principal connection on the associated principal bundle. The details don't matter. This is a standard construction. Just the fiber metric here, this psi is going to, we have a single warp product metric, and the scaling function is going to look like in my picture. So the length of this is large and the width of it is narrow. So think about the if you like, a surface of revolution you get by rotating that graph around the s-axis, and this will give you a picture of what the fibers look like. It looks like essentially a hollow, kind of long, thin, cigar-shaped kind of object. You need the largeness to facilitate the largeness of lambda to facilitate the surgery. You need the C to be small to control the curvature, which comes from the fact that you're doubling up a non-trivial disk bundle. So there's some kind of twisting going on in the bundle, which the geometry reflects. And C allows you, the smallness of C allows you to control the contribution that makes to curvature. So pretty obviously we have this symmetry. We can rotate about the S-axis in the picture, giving an SO2K symmetry, and we can flip around the ends, giving a Z2 symmetry. Okay, so let me try and draw a picture for what's going on here. So that's my picture, which I'll try and interpret for you. So I have this product, SA cross SB, and this product is what I'm kind of highlighting with my cursor here. Is this collection of SB spheres sitting over the base SA, and it's a trivial bundle, of course, topologically. So we have a projection map down, and we also have the map F, which is our degree D map, which takes SA onto this green thing here, which is my embedded manifold W, on which I'm going to perform surgery. Now, I'm wanting to choose my metric on my slice, my metric G, so that the SBs, which is this black slice here, and the W, that these meet orthogonally at every point. So then I mentioned that the SBs are given this cigar-shaped kind of metric. So what you see is something like in this picture in the top right. So these cigars are kind of twisting, they're kind of bending around the W somehow. Because if you cut them in half, what you have is a non-trivial disk bundle, or to say the same thing a different way, the bundle of equators, which is this yellow bundle you get, is non-trivial. However, overall, this sphere bundle is trivial. If you rounded those, if you were to squash those cigars down to spheres, what you would see is a trivial bundle. But you've elongated the spheres and you've kind of geometrically twisted them somehow. So you're seeing some twisting, which is there geometrically, but is not there topologically. So this is the picture to bear in mind for what I want for my metric G. Now, to do surgery, I need to think about what's going on, not just in this slice SA cross SB, but more generally in the ambient sphere. So I'm going to think about the normal bundle in the ambient sphere and think about a particular normal fiber. You have to bear in mind this picture is going on in every normal fiber to the bundle, but let me draw a picture of one of them. And this is the picture. So this red dot in the center is the point of W of which this is the normal fiber of. And the normal fiber can be foliated. It's just a vector bundle, of course. So the vector space there can be foliated into these concentric spheres. And we have a metric coming from our ambient metric, which locally is a product between the metric G I discussed and the metric in the T direction. So we have a normal disk metric, which can be expressed like this. Now, tau here is the kind of inward normal parameter. So we can express the normal disk metric like this. And you can write down explicitly, if you wanted to, what this metric HT, which is the metric on each of the normal spheres, actually is. And then what you do is you want to reparameterize this by introduce a scaling function, phi, like I'm indicating. And what this does is kind of, if you like, you push up through the bottom of my top picture and you pull out into a tube these normal spheres, so that that as you move upwards, the metric on these normal spheres becomes independent of the parameter, and what you end up with is a tube. So imagine cutting out a little bit of the center of that picture on top and then pushing out the rest into a tube. Now, geometrically, you have to keep track of what's going on. But to cut a long story short, and to cut a very long computation short, you can do this provided you choose everything correctly within two positive Ricci curvature, which is the curvature condition du jour. So to complete the surgery, then, you need to cut out the normal disk bundle and then glue something in to close off the gap. And you glue in, as I discussed earlier on, a disk cross sphere. And then you need to extend the metric over the thing you glue in, preserving the curvature condition. There's a problem here. And this goes back to my revolving cigar picture that I had a couple of minutes ago. That the metric you have on the boundary has the wrong symmetry if you want to extend it across this glue-in piece. And this is a bit of a problem. And the only way to really resolve it is to alter the geometry of the bundle on the boundary. So what you have to do, and I kind of indicated this earlier, if you kind of squash the cigars down to spheres, then you increase the symmetry from SO2K cross Z2 to SO2K plus 1. And that increase in symmetry allows you to extend this metric. The bundle geometrically kind of behaves non-trivially, but if you can round the spheres off, then geometrically it appears to be trivial, and then you can extend the thing as you would like. So you need to do this in 3 steps. Firstly, you scale these cigar-like fibers down to a suitably small level. That has the effect of magnifying the curvature, gives you more room in which to work. Then you can then start about changing the fiber shape from cigar to round. And then when you've done that, you can then untwist the metric and then extend over this gluing piece. So you need a shrink, rounding, and then untwisting kind of protocol to be able to do this extension. Of course, you've got to do that within this curvature condition, but it's actually fairly straightforward to show that you can do that. That's not difficult. And then this allows us to complete the surgery. Now, one thing I mentioned at the start is that surgeries depend on trivializations of the normal bundle. And in case you're interested in this, exactly the same argument can handle different trivializations, essentially with little or no change from what I've just discussed. Now, if anyone's still awake at this point, you might possibly remember my original metric picture which had some warp products in the end, had this dt squared plus g in the middle, and then had these transition regions between the kind of two, the middle bit and the end regions. And I didn't say anything about the transition region, but happily, one comment will suffice here, which is just as well since I'm nearly out of time, that in order to figure out what you need to do with the transition regions, it turns out that what you need to do is you need to shrink the fibers, change the fiber shape to round, untwist the metric, and then extend. And these are exactly the ideas which I had at the top of the screen. So it's not exactly the same, the context is slightly different, but the same philosophy and basically the same calculations works to define the metric in these transition regions too. So that was all I wanted to say. So just to summarize, in case people have lost track in the details, that essentially every highly connected manifold in dimension 4k plus 1 up to the potentially connected sum with a homotopy sphere, these all admit metrics of 2 positive Ricci curvature. Conjecturally, let me finish with this, that we conjecture that all these manifolds should admit positive Ricci curvature, but technically this is out of range at the moment, since we would either need to have a better understanding of how Ricci positive curvature behaves with respect to connected sums, and or a different alternative topological description of these manifolds, neither of which we have at the moment. So this is the best we can do. We can work with 2 positive Ricci curvature, and so that is all I wanted to say. So thank you for listening. I hope that was of interest to at least some of you.